Hello and a very warm welcome to the AI with Arun show. In today's episode, we'll embark on a deep dive into a critical transformation happening right now, the AI data center revolution. We'll explore how these specialized facilities are powering the future of AI, but also examine the significant challenges that they present. We'll cover the unique architecture, the cutting edge technologies involved, the dynamic market landscape, and the increasingly vital sustainability imperatives that are shaping this next era of digital infrastructure. Now we see a paradigm shift where the AI data centers are front and center. The rise of AI isn't just changing software, it's fundamentally reshaping our physical digital infrastructure. AI's insatiable demand for computational power has necessitated a new breed of facility, which is called the AI data center. These aren't your traditional data centers, they are powerhouses meticulously designed and purpose built for the unique and immense demands of AI and machine learning workloads, such as training incredibly complex models or running real time instances. Unlike traditional data centers focused on general tasks like web hosting or standard business applications, AI data centers present an evolution. They are optimized environments characterized by high demand computing hardware, advanced, often liquid based cooling systems, high throughput, low latency networks, and incredibly robust, increasingly sustainable power solutions. Now, over the next three slides, we'll look at how AI data centers and the traditional data centers are fundamentally different. So let's get started. Now, this table illustrates the difference is stark. Traditional data centers focus on general computing and business applications, handling diverse but generally less compute intensive workloads. AI data centers, conversely, are built for the intense, data heavy, parallel processing required for AI model training and inferences. This difference in purpose dictates the hardware, primarily CPUs in traditional data centers versus a heavy reliance on GPUs, TPUs, and other specialized AI accelerators alongside CPUs in AI facilities. This leads to extreme power densities in AI centers. Think 40 to over 100 kilowatt per rack, potentially exceeding 200 kilowatts soon, compared to a moderate 3 to 12 kilowatts traditionally. Consequently, cooling shifts from primarily air-based methods to advanced techniques, where liquid cooling becomes essential. Networking moves from standard Ethernet to high-speed, low-latency fabrics like Infiniband, advanced Ethernet with ROCE, or even optical circuit switching. Storage must handle massive unstructured datasets using high-performance solutions. And finally, the cost drivers shift dramatically from standard hardware and moderate power to expensive accelerators, advanced cooling and networking, and extremely high power consumption. It is crucial to understand this isn't just an incremental upgrade, it's a complete reimagining of data centers infrastructure driven by the unique computational physics of AI. Now let's look at the hardware engine. Now, at the heart of the AI data centers lies specialized compute hardware. GPUs or graphic processing units, originally for graphics, have become the workhorse for AI training, particularly deep learning. Companies like NVIDIA dominate the space with architecture like Hopper and Blackwell, featuring thousands of cores perfect for parallel tasks like matrix math. Data center GPUs are distinguishable by large amount of high bandwidth memory or HBM as we call it, crucial for holding vast model data. Then we have TPUs, the tensor processing units, which are custom designed ASICs from Google, specifically optimized for neural networks computations used in frameworks like TensorFlow, PyTorch, and JAX. They incorporate specialized hardware like matrix multiply units or MXUs for high efficiency and are often paired with Google's unique optical circuit switching network technology in their cloud infrastructure. Beyond these, other accelerators also play a role. The ASICs offer peak efficiency for specific tasks. FPGAs provide reconfigurable flexibility, used notably by Microsoft, and NPUs are often integrated with CPUs to accelerate AI performance. Of course, these powerful processors are useless without rapid data access. This necessitates substantial high-speed memory like HBM integrated directly with accelerators, fast NVMe SSDs for storage, and petabyte scale storage systems. The key takeaway here is a significant trend away from general purpose CPUs towards these domain specific architecture, which are essential for achieving performance needed for modern AI. This specialization is often driving major cloud providers like Google, AWS, and Microsoft to invest heavily in developing their own custom silicon to optimize performance and diversify their supply chains. Now let's look at the impact on data. Now, if accelerators are the engine, the network fabric is the critical highway enabling large scale AI, especially during distributed training. Network bottlenecks can severely cripple performance, effectively wasting millions in compute investment. Therefore, AI data centers demand networks with two key characteristics: massive bandwidth. We are talking 400 to 800 gigabytes per second per link today, with 1.6 terabytes per second and beyond on the horizon. And ultra low latency, where delays measured in microseconds or even nanoseconds matter significantly. Now, three main technologies compete in this space, each with trade offs. Infiniband, historically dominant in high-performance computing and AI, offered the lowest latency, down to 90 nanoseconds, a lossless fabric design, and a native RDMA support. NVIDIA is a key player here, which raises cost and potential vendor lock-in concerns. Ethernet, the familiar standard, is rapidly closing the performance gap. Enhanced with RDMA over converged Ethernet, which is called ROCE, achieving higher speeds like 800G and benefiting from collaborative efforts like the Ultra Ethernet Consortium. It offers cost effectiveness, openness, and operational familiarity, making it increasingly attractive, especially for hyperscalers. And then there is Google's unique approach, which is optical circuit switching or OCS, using tiny mirrors to physically steer light signals. OCS bypasses electrical switching, achieving potentially dramatic reductions in latency, power consumption, reportedly less than 5% of system power and cost. Its key advantage is dynamic reconfigurability, allowing the network topology to adapt on the fly. Designing these networks also requires specialized topologies like fat trees or Google Torus, optimized for massive east-west traffic between compute nodes and managing significantly higher fiber optic cable density, potentially 4 to 5 times more than traditional setups. Now let's look at some of the advanced cooling strategies. The immense power drawn by AI hardware directly translates into a massive heat problem. We are talking extreme heat densities concentrated in small areas. Traditional air cooling, the standard for years, simply cannot cope efficiently or effectively when rack power densities climb above 40 kilowatts. Inadequate cooling leads to performance throttling, reduced reliability, and even hardware failures. This makes advanced cooling, particularly liquid cooling, an absolute necessity. Liquid cooling leverages the superior heat capacity of fluids to transfer heat more efficiently than air. The most common approach today is direct to chip or DTC, where liquid coolant flows through cold plates mounted directly onto the hottest components like GPUs and CPUs. A more radical approach is immersion cooling, where entire servers are submerged in a non conducive dielectric fluid. This offers the highest potential cooling efficiency, but faces challenges like the cost and the environmental profile of the fluids, maintenance complexities, and limited large scale deployment so far. A crucial trend driven by both sustainability and the sheer amount of heat generated is heat reuse. Capturing this waste heat to warm buildings, support district heating, or for industrial processes turns a liability into a valuable resource. Implementing these advanced cooling methods requires significant changes to data center infrastructure, piping, pumps, specialized racks. Furthermore, the substantial water consumption associated with some cooling methods raises concerns about water scarcity, marking water usage effectiveness or WUE a critical metric alongside PUE, the power usage effectiveness. Consequently, site selection for AI data centers must now carefully consider local climate, water availability, and the potential for heat reuse partnerships. Now, let's look at the holistic design imperatives. Bringing these elements together, designing an effective AI data center requires a holistic approach addressing several key imperatives. First, managing extreme power density. This means robust electrical infrastructure, high capacity distribution units, reliable UPS systems, backup generation. Designing for densities exceeding 40, even 100 kilowatts per rack. Energy efficiency, measured by power usage effectiveness or PUE, is paramount, and systems must handle the highly variable power demands of AI workloads. Power availability itself is becoming a major bottleneck in popular regions. Second, an integrated cooling strategy is non-negotiable. Liquid and hybrid cooling systems are becoming standard. Facility design choices like wider aisles or locating in cooler climates for free cooling play a role. And increasingly, AI itself, through AI ops, is used to dynamically optimize these complex cooling systems for maximum efficiency. Third, the network architecture must be meticulously planned for high performance. This involves handling massive east-west traffic, choosing appropriate topologies like FAT-free or OCS, and managing the extreme physical fiber density required. Finally, ensuring scalability and flexibility is vital in the fast-moving world of AI. Modular designs using prefabricated units allow for faster deployment and incremental expansion. Software-defined infrastructure provides agility through programmatic control of resources. Hybrid cloud strategies offer burst capacity and specialized services, and future-proofing design to accommodate the next generation hardware is crucial. Ultimately, building successful AI data centers demands breaking down traditional silos and tightly integrating IT infrastructure decisions with facility engineering from the very beginning. Let's look at the software ecosystem, which is essentially orchestrating the intelligence layer. Now, beyond the hardware and the physical facility, there is a sophisticated software ecosystem that is essential to harness the power of AI data centers. This stack includes AI frameworks, orchestration tools, and data management platforms. AI frameworks and libraries are the fundamental tools developers use to build, train, and deploy models. Key players include Google's TensorFlow, known for its production robustness and TPU optimization. Meta's PyTorch, popular in research for its flexibility and dynamic graphs. Kera's a user-friendly high-level API, and JAX gaining traction for high-performance research, especially with TPUs. NVIDIA also offers specialized frameworks like NeMo for generative AI. Managing the complexity of distributed AI workloads requires powerful workload orchestration and management tools. AI orchestration platforms coordinate entire AI systems, models, data pipeline, resources. Cluster management tools like Scrum or Kubernetes, often augmented with platforms like NVIDIA's Run AI, allocate scarce compute resources like GPUs. Data orchestration tools like Apache Airflow, Daxter, or Perfect automate the critical data pipelines. And MLOps platforms such as AWS SageMaker or Google Vertex AI streamline the entire machine learning lifecycle from development to deployment and monitoring. Finally, data management platforms and pipelines are crucial as data is the lifeblood of AI. Efficient pipelines automate data ingestion, pre-processing, and validation. High-performance storage solutions, including NVMEs, SSDs, parallel file systems, and increasingly vector database essentials for techniques like retrieval augmented generation or RAG. These are required to handle massive data sets. Robust data governance and metadata management are also critical for quality, security, and compliance. The intricate software ecosystem is indispensable for developing, deploying, managing, and optimizing AI workloads efficiently, reliably, and responsibly at scale. Now, let's look at the market explosion. What does it mean in terms of size, growth, and segmentation? The market for AI data centers is experiencing nothing short of an explosion. This surge is overwhelmingly driven by a rapid adoption of AI technologies across virtually every sector, with generative AI like ChatGPT and Gemini and image generators acting as the primary catalyst. While exact market size figures vary between research firms due to differing definitions, the growth trajectory is undeniable. Projections consistently show extremely high compound annual growth rates, typically between 25 and 40% for the coming years. To give you a sense of scale, estimates place the market anywhere from $5 and $15 billion in 2024, potentially soaring to anywhere from $60 billion to over $150 billion by early 2030s. Now, looking at market segmentation, hardware currently dominates, accounting for over half the market, driven by demand for compute accelerators like GPUs and TPUs and advanced thermal management solutions. Hyperscale data centers are run by the major cloud providers, represent the largest data center type segment, needing a massive scale for model training and cloud AI services. Cloud based deployment holds the largest share, reflecting the preference for flexibility and cost efficiency. Key industry verticals driving demands include finance, IT and telecom, healthcare, retail, and automotive. Geographically, North America, led by the US, currently holds a dominant market share, exceeding 35 to 40%. However, significant growth is expected in the Asia Pacific region and Europe, partly due to cloud constraints emerging in established North American hubs and strategic investments elsewhere. It's clear that AI is not just a segment driver, it's a primary force propelling the growth of the entire global data center market. Now, the AI data center ecosystem is dynamic and complex web involving a diverse range of players. At the top are the hyperscalers, the Google Cloud, AWS, Microsoft, Azure, Meta. They are the largest drivers of demand, building vast infrastructure for their own AI service and foundational models, while also being the primary providers of AI platforms and infrastructure to others. Their scale allows for huge market expenditures. Figures like 75 billion for Google and 80 billion for Microsoft have been cited for upcoming investments, much directed at AI, and the development of custom silicon like Google's TPUs or AWS Trainium chips. Chip manufacturers are critical. NVIDIA holds a commanding position, especially in GPUs for AI training and Infiniband networking. AMD is a key competition with its GPUs and CPUs, while Intel remains significant with CPUs and its own AI accelerators. Co-location providers like Equinix, Digital Reality, and Cyrus One supply the essential physical facilities, space, power, cooling. These are crucial partners, increasingly adopting their sites for AI's high density requirements and often leasing significant capacity to the hyperscalers. A newer category in this special AI providers, such as CoreWeave and Lambda Labs, they focus specially on offering high performance GPU capacity, catering to users needing large clusters who might find hyperscaler options constrained or less cost effective for specific AI tasks. Now, supporting these are numerous infrastructure and equipment providers providing power systems like Schneider Electric, Vertiv, cooling, Danfoss, networking like Cisco and Arista, servers like Supermicro, Dell, HPE, and storage like Samsung. Finally, system integrators and construction firms design and build these complex facilities. This ecosystem is defined by intense investments, competition, strategic partnerships like those for heat reuse or AI ready facility certifications, and critical dependencies between players. Now, several powerful trends are currently shaping the AI data center landscape. First and foremost, generative AI is the undisputed primary demand driver. The race to build and deploy large language models and other generative AI tools is fueling the need for massive training capacity and increasingly scalable infrastructure for inference as these models are put to use. Secondly, there is intensifying focus on sustainability. The enormous energy and water consumption of AI data centers is under scrutiny, driving efforts towards renewable energy sourcing, improving energy and water efficiency, PUE and WUE as we call it, adopting energy saving liquid cooling, and implementing heat reuse strategies. Sustainability is rapidly becoming a core design principles. Third, we see the expansion of edge AI. Processing AI inferences closer to the data source reduces latency for real time applications and enhances data privacy. This requires deploying distributed edge data centers or powerful edge devices, often working in tandem with larger central facilities. Fourth, hybrid and multi cloud strategies are now standard practice. Organizations combine private infrastructure with public cloud services for flexibility, cost optimization, and risk mitigation. We have even seen some strategic cloud repatriation of workloads. Now, fifth, liquid cooling is going mainstream, transitioning from a niche technology to a requirement for high density AI. Sixth, increased automation and AI ops are essential for managing complexity, optimizing cooling, power workloads, and enabling predictive maintenance. Seventh, modular data center construction is gaining traction for faster deployment and scalability. And finally, the concept of AI factories is emerging. Highly integrated supercomputing scale facilities offered as a service for end to end AI deployments. These trends are interconnected, creating a complex optimization challenge for the industry. How do you maximize performance while minimizing cost, ensure reliability, and yet meet sustainability goals and maintain flexibility in the face of rapid AI adoption? Now, despite the excitement and growth, the AI data center revolution faces significant challenges. The most common, prominent one is the extreme energy consumption. Now, individual AI accelerators can draw over 700 to 1200 watts each, leading to rack densities of 40, 100 kilowatts or more. This results in staggering overall energy use. Projections suggest global data center electricity demand would double by 2026 to 2030, largely due to AI, potentially consuming a significant percentage of national and even global electricity supply. This strains grids, inflates operational costs, and creates a massive carbon footprint if powered by fossil fuels. Directly linked to these is intense heat generation. This concentrated heat overwhelms traditional air cooling, risking performance throttling and hardware failures. Implementing the necessary advanced cooling, liquid cooling, adds significant cost and complexity. The financial costs are substantial. Capital expenditures or capex are high due to expensive specialized hardware like GPUs, TPUs, high speed interconnects, and liquid cooling systems. Building facilities for extreme density also increases construction costs, potentially running into billions of large clusters. Operational expenditure, OPEX, are dominated by enormous electricity bills for powering compute and cooling. Beyond cost, the environmental impact is a major problem. The large carbon footprint from energy use is significant. Training a single large model can equate to the lifetime emissions for several cars. Water consumption for cooling is vast, potentially straining local resources in water scarce regions. An average data center can use hundreds of thousands of gallons daily. Finally, manufacturing the complex hardware involves resource depletion and rapid upgrade cycles continues to a growing e-waste problem. These challenges are deeply interconnected, making sustainability not just desirable, but a fundamental necessity for the industry's future. So, what is driving this massive investment and build out? A diverse range of powerful applications. The single biggest driver right now is the training and deployment for large language models, LLMs, and generative AI. Training foundational models like GPT-4, Gemini, or Llama requires processing trillions of data points on a huge clusters of accelerators for extended periods. These models power everything from chatbots and content generators to enterprise productivity tools. Scientific computing and research is another major area. Data centers provide the horsepower for breakthroughs in drug discovery and genomics, like protein folding simulations, complex climate modeling, material science, and physical simulations. AI accelerates these processes and helps uncover new insights. Cloud AI services, or AI apps, offered by providers like AWS, Azure, and GCP, are built on their data center infrastructure. They provide business access to pre trained models, development platforms like SageMaker or Vertex AI, and raw GPU, TPU compute instances, democratizing AI capabilities. Developing autonomous systems, particularly self driving vehicles, is incredibly compute intensive. This involves processing petabytes of sensor data, training complex perception models, and running vast simulations. Companies like Neuro and Toyota's Woven rely heavily on the infrastructure. Enterprises are integrating AI across their operations for predictive analytics, process automation in finance or customer service, personalization, cybersecurity, and deeper data analysis. Finally, AI is being used to optimize data center operations themselves. AI ops tools help manage workloads, optimize power and cooling. Google reported significant cooling cost reductions using AI, perform predictive maintenance, and enhance security. The common thread across all of these use cases is the need for massive computational power, efficient processing of enormous datasets, and often low latency responses. Precisely what AI data centers are designed to deliver. Now, the AI data centers is evolving incredibly fast. Looking ahead, several key innovations and trends are poised to reshape the landscape. In chip design, while GPUs and TPUs lead now, we are seeing active exploration of novel architecture aimed for better performance and drastically improving energy efficiency. Neuromorphic computing, inspired by human brains structure using spiking neural networks, promises significant energy savings, especially for edge AI. Companies like Intel and IBM are already developing neuromorphic chips. Another exciting area is optical computing or photonics, which uses light instead of electrons. This offers potential advantage in speed, bandwidth, and much lower energy use for key AI operations like matrix math. While full optical computers are early stage, optical interconnects like co-packaged optics or Google's OCS are already appearing. Cooling technology will continue to advance. We'll see broader adoption and refinement of liquid cooling, hopefully using more environmentally friendly fluids. And integrated heat reuse is expected to become standard practices, designing data centers as integral parts of local energy ecosystems. Energy efficiency improvements must happen across the entire stack. This includes most efficient hardware, optimizing AI software and algorithms to do more with less computation, using AI ops for dynamic operational efficiency, and smarter data center design, incorporating renewables and efficient power distribution. Edge AI integration will accelerate. Future architecture will likely be hybrid, combining large central training facilities with distributed edge networks for real time inference. Technologies like federated learning and edge native models will be key. Finally, software defined and composable infrastructure will continue to advance. Abstracting hardware via software allows for greater flexibility and automation. Composable infrastructure, dynamically pooling resources like GPUs or memory on demand, promises even greater agility and efficiency. The future truly hinges on a holistic approach, simultaneously pushing performance while aggressively addressing cost and sustainability through continuous innovation across all these areas. In conclusion, the AI data centers represents a truly transformational evolution in digital infrastructure, essential for unlocking the full potential of artificial intelligence. They make a significant departure from traditional designs driven by the unique demands of AI workloads. However, this revolution presents a dual reality. We see explosive market growth and incredible technological opportunity, but these are coupled with formidable challenges, staggering energy and water consumption, substantial financial costs, and significant environmental impacts. The path requires a critical balancing act. The relentless pursuit of greater computational performance must be carefully weighed against the imperatives of operational efficiency, cost effectiveness, and environmental stewardship. Sustainability is no longer an afterthought, it's a fundamental required for responsible growth. Achieving this balance demands continuous, holistic innovations across the entire ecosystem, from chip design and software algorithms to cooling techniques, energy management, facility operation, and collaborative partnerships. How successfully we navigate this complex interplay will ultimately determine the pace, scale, and nature of AI's integration into our world. Building a future that's both powerful and sustainable is the defining challenge and opportunity before us. With that, we come to the end of the show. Thank you for watching the AI with Arun show. Like, share, subscribe, and let us know what you think in the comments below.